Hello everyone, and thanks for having me today. I am really sorry I could not attend the meeting in person, but here I will talk about the direct test algorithm that is under development and study at CNES in order to retrieve sea surface temperature for TRISHNA. First of all, a quick reminder on the equation we need to solve to access surface emissivity and temperature. The problem to solve is a non-deterministic process, and for any spectral band for a given sensor, what we know is the TOA radiation measured by the satellite in green in the equation, the three atmospheric components in blue, which are computed from a radiative transfer code, which will be RT-top for TRISHNA. And what we don't know and want to access are the emitted surface radiation, which depends on the surface temperature and the surface emissivities. In that problem, we then have k+1 unknowns for k equations, and we need additional information to solve the equation. Different algorithms are classically used to derive surface temperature and emissivities. First, empirical split window methods derive surface temperature from measurements in two adjacent TIR channels in the 10-12 micrometer interval. The hypothesis under these algorithms is that most natural surfaces have a flat emissivity spectrum in that TIR domain. Split windows are commonly used over oceans to compute sea surface temperature, and split window needs first to be calibrated and requires a priori information on surface emissivity. This algorithm was initially developed for Aster sensor and relies on surfaces' empirical relationship between the spectral contrast and the minimum emissivity of the observed spectra. To run, TESS requires first an atmospheric correction, and it is known that this algorithm is not adapted for surfaces with low spectral contrast such as vegetation or water. Direct test algorithm is developed at CNES and relies on a spectral database of emissivity. The idea is to calculate the surface temperature corresponding to the radiation measured by the satellite for each pixel and for each material of the spectral library. If temperatures for a given material in the n spectral bands are consistent, the material is considered valid, and so is the temperature. With direct tests, we can also use coherent reflectance criterion in the visible bands to get rid of the obvious non-consistent materials. Direct tests need atmospheric correction at first, and obviously depends on the spectral library that is used. For a dedicated application over water, direct tests can then be used with a dedicated spectral library made of only water spectrum. Here is an overview of the algorithm chain that is developed for TRISHNA on CNES side. Over water, we have two options today. The first option is to use a chain called TRISHNA, which combines atmospheric data and radiative transfer computations done with RT-top, and then temperature and emissivity separation with the algorithm direct tests, relying on a spectral water database. The second option is to use a split window algorithm. In order to choose algorithm for TRISHNA, we made different comparisons of the algorithms. To begin with the result, we first compared tests and direct tests on end-to-end simulation where we managed all the data, the instrument and atmospheric uncertainties too. The synthetic reference dataset is made of water spectrum and transposed to the top of atmosphere using direct radiative transfer with representative atmospheric data, which yields to a top of atmosphere reference dataset. Direct test or test is then applied after the application of both atmospheric and instrument uncertainties. When all the spectral library made of vegetation, soil, water, and urban materials is used, here we got significant bias for direct test and test. But when we constrain the spectral library to water spectrum, as we know we are looking at water, direct test showed no bias anymore, and a theoretical RMSE reduced to 0.5 Kelvin. And in that case, the RMSE came from the instrument and atmospheric uncertainties only. Made comparison to evaluate the performances to retrieve sea surface temperature on actual in situ data. We evaluated direct test to in situ data measured on Lake Tahoe and kindly provided by the GPL. When we used the complete spectral library for direct tests than the ones we will use to retrieve the land surface temperature, direct test gave sea surface temperature with around 0.7 Kelvin bias and 0.9 Kelvin RMSE compared to Lake Tahoe temperature measurements. When we run direct tests with a water emissivity database, as we know we worked on water, we got no bias and an RMSE of 0.65 Kelvin. This remaining RMSE can be the result of uncertainties in the atmospheric profiles we used, or the result of a failing in the interbond calibration, because by nature, direct tests cannot be robust to interbond calibration. In order to conclude, the algorithm direct test allows to process an atmospheric correction, and we noticed that all the error comes from instrument and atmospheric uncertainties. So we are working on the possibility to perform the inversion over a noisy atmospheric library in place of the spectral emissivity library, assuming water emissivity is known. Direct test performances for sea surface temperature retrievals are promising, but further comparisons with specific and water-dedicated split window algorithms are needed before making a choice for TRISHNA. To do so, we are currently processing with the Ifremer Institute a comparison of split window NL-SST algorithm and direct test algorithm on eco-stress data collocated with various images in order to choose the best algorithm for TRISHNA sea surface temperature products. Thank you for your attention.